Hello everyone. Here's a fun thought to start. Why does a clock's pendulum never get tired of swinging back and forth? Because it just loves going back to its favorite spot, the mean position. Now, let's dive into what makes motions like these so interesting. Motion that repeats itself after regular intervals is called periodic motion. Think of the second hand on a clock, ticking around in a circle over and over again. Oscillatory motion is a special type of periodic motion where the object moves back and forth across a central mean position, like a child on a swing or a mass on a spring. But here's a neat detail: every oscillatory motion is periodic, meaning it repeats regularly, but not all periodic motions are oscillations. For example, a particle moving in a uniform circular path is periodic because it repeats every circle, but it's not oscillatory since it doesn't move back and forth along a line. In oscillations, the displacement from the mean position, the velocity, and even the acceleration change smoothly in a wave-like or sinusoidal pattern over time. We can describe the displacement mathematically as x of t equals a times sine of omega t plus phi, where a is the maximum displacement called amplitude, omega is the angular frequency, and phi is the phase constant that tells us where the motion started. Importantly, all these quantities repeat exactly after a fixed period t, which means if you look at the motion time t seconds later, the displacement is the same as before. Mathematically, x of t plus t equals x of t. From this, we derive that omega equals to times pi divided by the period t, showing the tight relationship between these values. So next time you see a pendulum or a bouncing spring, remember you're watching nature's own clockwork in action, repeating itself perfectly thanks to the physics of periodic and oscillatory motions. Now let's talk about some real-world stars of oscillatory motion. Imagine a spring loaded up with a weight, or a simple pendulum swinging with a small amplitude, or even the strings of a guitar vibrating to produce sound. What do they all have in common? They all involve restoring forces that act to pull the object back toward its equilibrium or mean position whenever it's displaced. This restoring force is the secret behind their periodic back and forth dance. If you look closely, the position and speed of these objects change over time in a repeating way, just like those sine waves we talked about. In fact, their motion can be modeled using harmonic equations, where the restoring force is expressed as F equals minus k times x. This means the force is proportional to the displacement x, but acts in the opposite direction to pull the object back. This law is famously known as Hooke's law. When the restoring force obeys Hooke's law, the motion is called Simple Harmonic Motion, or SHM, and it produces smooth sinusoidal oscillations that we see in these examples. Working with small amplitude oscillations helps us simplify the math, reducing to linear differential equations and straightforward sine and cosine solutions. That's why we mostly focus on small swings and tiny vibrations in physics classes. It keeps the equations neat and the concepts crystal clear. So next time you pluck a guitar string or watch a tiny pendulum swing, remember they're perfect examples of oscillatory motion governed by the elegant restoring forces of nature. Let's zoom in on the heart of simple harmonic motion, or SHM, which is the queen of oscillations in physics. The defining feature of SHM is that the net restoring force acting on the particle or object is directly proportional to its displacement from the mean position and points straight back towards that position. In math speak, this is written as F equals minus k times x, where F is the restoring force in newtons, k is a positive constant known as the force constant or spring constant in Newton per meter, and x is the displacement in meters. The negative sign tells us the force opposes the displacement, always pushing or pulling the object back to equilibrium. This neat relation leads us to an important equation of motion a second-order differential equation that says the second derivative of x with respect to t plus omega squared times x equals 0, where omega is the angular frequency of oscillation given by the square root of k divided by m, with m being the mass in kilograms. Solving this differential equation tells us that the displacement x as a function of time t is sinusoidal. X of t equals a times sine of omega t plus phi, where a is the amplitude and phi is the phase constant setting the starting point of the motion. So, the object oscillates back and forth smoothly over time. An important insight here is that the total mechanical energy in this idealized system remains constant. No energy is lost, but it keeps swapping seamlessly between kinetic energy when the object speeds through equilibrium and potential energy stored when it's farthest from equilibrium. This interplay of forces and energy makes SHM not just a math problem, but a beautiful dance that you can see in many real-world oscillations. Time to peek under the hood and explore the mathematical details of simple harmonic motion. Recall that displacement from the mean position varies sinusoidally and can be expressed as x of t equals a times cosine of omega t plus phi, or sometimes as sine, depending on the system's starting conditions. Next, velocity, which is how fast the displacement changes with time, is found by taking the first derivative of displacement. So, velocity v of t equals the derivative of x with respect to t, that is, v of t equals negative a times omega times sine of omega t plus phi. This tells us velocity also varies sinusoidally but is shifted in phase compared to displacement, and the negative sign shows the direction changes accordingly. Acceleration, the rate of change of velocity, comes from the second derivative of displacement with respect to time. That gives us a of t equals negative a times omega squared times cosine of omega t plus phi. Notice how acceleration is directly proportional to displacement but always acts in the opposite direction, consistent with the restoring force. The maximum or peak values for velocity and acceleration are v max equals a times omega and a max equals a times omega squared, respectively. They tell us how fast the object moves at its fastest and how sharply it turns around at the extremes of its path. Importantly, acceleration always points towards the equilibrium position, pulling the object back, which is why the motion continues smoothly without flying off in some random direction. These mathematical relationships reveal the elegant harmony underlying simple harmonic motion, helping us predict exactly how objects will move over time. Now, let's understand some key terms in oscillations that determine how and when the object moves. First up is phase, often denoted by the Greek letter phi. Phase tells us the initial angle or starting point of the oscillation in its cycle and changes linearly over time. At any time t, the phase is given by omega times t plus phi 0, where phi 0 is the initial phase at time 0. Phase helps us know exactly where in its swing the object is, like telling what number a clock's hand points to. Next, angular frequency omega defines how quickly the oscillation happens. It's related to frequency f and period t by omega equals to times pi times f, or equivalently, omega equals to times pi divided by t. Here, t is the time period, the time taken for one complete cycle of oscillation measured in seconds, and f is frequency in hertz or cycles per second. For systems like the spring mass setup, the time period t depends only on the system parameters. It equals to times pi times the square root of m divided by k, connecting mass and spring constant neatly to how fast it oscillates. Finally, when we look at two different simple harmonic motions acting together, the difference in their phases, called the phase difference, determines whether they add constructively, making a bigger combined oscillation, or destructively, cancelling each other out. This phase relationship is vital in many phenomena, from sound waves creating beats to electronics and even quantum mechanics. So, understanding phase, angular frequency, and time period helps us master not just single oscillations but the rich world when many oscillations meet. Let's zoom into the energy story behind simple harmonic motion, which is as fascinating as the motion itself. First, potential energy stored in the system depends on how far the object is from its equilibrium position. We express this as U equals 1/2 k times x squared, or equivalently, U equals 1/2 m times omega squared times x squared, meaning the energy increases quadratically with displacement. When the object is at maximum displacement, potential energy peaks because the spring or system is maximally stretched or compressed. Next, kinetic energy, which is due to the object's motion, is given by k equals 1/2 m times v squared. Using our SHM relationships, we can rewrite this as k equals 1/2 m times omega squared times the quantity a squared minus x squared, showing that kinetic energy is maximum when the object passes through equilibrium, where displacement x is 0 and 0 at the turning points. The beautiful part is that the total mechanical energy, which is the sum of kinetic and potential energy, remains constant throughout the motion in an ideal system without friction. Mathematically, this is E equals 1/2 m times omega squared times a squared, indicating the total energy depends only on the mass, angular frequency, and amplitude. Energy smoothly exchanges between kinetic and potential forms as the object swings back and forth, but the total energy graph would be a flat horizontal line if plotted against time, showing conservation. This energy interplay is why these oscillations can continue without fading away, at least in the perfect world of physics problems. To wrap up today's introduction to oscillations, let's quickly revisit the key equations and ideas that form the backbone of simple harmonic motion. Displacement x as a function of time t is expressed as a times sine of omega t plus phi, telling us where the object is at any instant. The velocity v of t is the first time derivative of displacement and can be written as a times omega times cosine of omega t plus phi. Then acceleration a of t is the second derivative, given by negative a times omega squared times sine of omega t plus phi, showing it always points back toward equilibrium. The time period t, or the time taken for a complete oscillation, equals to times pi divided by omega. Total mechanical energy E in SHM is 1/2 m times omega squared times a squared, which remains constant. What makes SHM special is this linear restoring force F equals minus k times x, its smooth sinusoidal variation, and perfect energy conservation within the system. All these quantities repeat after a fixed time t, with phase setting the initial start and amplitude defining how far the system moves from the mean position. Understanding these foundational principles is crucial because they set the stage for more advanced topics like damped oscillations and forced oscillations that you'll explore next. So that's it for today's concept. Remember, physics gets even more fun when you can laugh and learn at the same time. See you in the next session.